When we had stopped last time, we were looking at electrocyclic reaction. And we had first of all differentiated between the three types of pericyclic reactions. In an electrocyclic reaction, you go from n pi to n minus 1 pi. In a cycloaddition, you go from n pi to n minus 2 pi. In a sigmatropic, there is no change in number of double bonds, no change in number of rings. Then we had looked at the features of a pericyclic reaction. And the number one important feature is it must involve a cyclic transition state, and reaction should take place in a concerted manner. Okay. Then we had discussed question of conrotatory and disrotatory. In a conrotatory, you move both bonds in clockwise manner or move both bonds in anti-clockwise manner. That's your conrotatory process. In a disrotatory process, you move the two thumbs in opposite directions, either both upwards or both downwards. Then we had said that from many experiments involving 4q electrons, the thermal reaction is conrotatory, the photochemical reaction is disrotatory. And when it involves 4q plus 2, the picture is just the opposite. Then we had illustrated two important principles, and that is, in a thermal reaction, you always go from less stable to more stable. In the photochemical reaction, the important process is you go from more conjugated to less conjugated, because the more conjugated system absorbs UV at longer wavelength. Okay. Then we had started looking at orbitals, and we had looked at the orbitals. This is your ethylene orbitals pi and pi star. When we combine these two, you combine 2 pi orbitals, you get psi 1. You combine them in a negative manner, pi 1 plus pi 2, you will get your second orbital, that is psi 2. You combine 2 pi star orbitals in a positive manner, pi 1 star plus pi 2 star gives you psi 3, and you combine them in a negative manner, you get psi 4. Then we had combined these two butadiene orbitals to get the 8 orbitals of octatetraene. All right. Finally, we had introduced the concept of nodes. In your orbital of lowest energy, there is no node. In your second orbital, there is one node. A node is a position when you have a sign change. In your third orbital, there will be 2 nodes, and in your fourth orbital, there will be 3 nodes. In your 100th orbital, there will be 99 nodes. Okay. What if I represent it as a wave? then what do I see? If I can join all orbitals with positive sign, then there is no sign change. When I connect positive orbitals now, that is the point where you have a node. If I combine positive orbitals here, that will be your two nodes. Okay. So, that was the concept of nodes. Why did we introduce the concept of nodes? Because when we want to write hexatriene, we have a problem. How are we going to combine to get hexatriene? So, in the hexatriene picture, we have to use the concept of nodes. Okay. If I look at these orbitals, what is this? I am writing the signs on the upper face. All right. What do I see? Obviously, I see that there is one node. So, if there is one node, what is this orbital? It is the second orbital. So, this is going to be your second orbital. How many nodes are there in this orbital which I have written? 4 nodes. 1, 2, 3, 4 nodes. So, this is your obviously your fifth orbital. There is no node in this. Therefore, this is your first orbital. How many nodes are there in this? 2 nodes. 1 node here, 1 node here. Therefore, this is your third orbital. One, 2, 3, 4, 5 nodes. Therefore, this is your sixth orbital. How many nodes? 1, 2, 3 nodes. Therefore, this is your fourth orbital. We omitted all the mathematics from this and we wrote these orbitals and decided what is the level by looking at the number of nodes. Okay. When we look at valence bond theory, what do we say? Number of electrons in the outermost shell is going to determine valency. If carbon has 4 electrons in the outermost shell, to become octet, it requires 4 electrons. Therefore, carbon has valency 4. Nitrogen has 5 electrons in outermost shell, therefore, it has valency 3. Oxygen has 6, valency 2. So, in valence bond theory, the number of electrons in outermost shell is important. In orbital theory, that is going to be the important feature. What is this? Highest occupied molecular orbital. Okay. So, in valence bond theory, the highest occupied molecular orbital is important, or the second orbital that we worry about is the lowest unoccupied molecular orbital. sometimes also called the lowest vacant molecular orbital. Okay. So, how can I talk about this? If I worry about the safety of India, then what happens in Maharashtra, what happens in Karnataka does not matter. What we worry about are what are the states on the border. Okay, so, you worry about Rajasthan, you worry about Punjab, you worry about Bengal, if you worry about the northeast. Why? Because that is the border where you may have problems. All right. So, we must know how to draw HOMO. All right. So, let us look at this. In ethylene, there are two orbitals. So, this is the highest occupied molecular orbital, this is the lowest unoccupied molecular orbital. So, how do I write HOMO? Plus and plus. Then you look at butadiene. What do we see in butadiene? We have 4 orbitals. Your highest occupied molecular orbital is this, plus, plus, minus, minus. You look at hexatriene. How many orbitals are there? 6 orbitals. So, orbital number 3 is going to be your HOMO. What is the picture in orbital number 3? Plus, plus, minus, minus, plus, plus. So, even without knowing anything, if I ask you to write HOMO, it is very easy. Plus, plus, minus, minus, plus, plus, minus, minus, plus, plus, minus, minus. Do this process, you will be in a position to write this. So, if you take 10 electrons, plus, plus, minus, minus, plus, plus, minus, minus, plus, plus. If you take 12 electrons, plus, plus, minus, minus, plus, plus, minus, minus, plus, plus, minus, minus, very simple. Okay. Can we have a simple way to get at LUMO? Pi is your highest occupied molecular orbital, your anti-bonding orbital is plus and minus. When I look at butadiene, what is the picture? Plus, minus, minus, plus. When I look at hexatriene, 6 orbitals, your highest is number 3, your lowest unoccupied molecular orbital is number 4. So, what is the picture? Plus, minus, minus, plus, plus, minus. If I look at 8 electrons, I use this concept. Plus, minus, minus, plus, plus, minus, minus, change the sign. If I look at 10 electrons, if I look at 12 electrons, so it is very important for us to understand this very simple idea. How to write HOMO, how to write LUMO. Even you need not write all the orbitals. All you have to do, write HOMO immediately, plus plus, minus minus, plus plus, go on. You want to write LUMO, plus, minus minus, plus plus, minus minus, plus plus, change the sign minus. That is the picture that you get. All right. Now, let us look at something in this. What are the signs of the two end orbitals in butadiene, plus and minus? Okay. So, let me write it like this. Plus, plus, minus, minus. If the end orbitals have opposite signs, the reaction is going to be conrotatory. End orbitals have opposite signs, reaction is going to be conrotatory. End orbitals have same sign, reaction is going to be disrotatory. 8 electrons, end orbitals have opposite sign, so reaction is going to be conrotatory. 10 electrons, end orbital have same sign, reaction is going to be disrotatory. End orbitals have same sign, reaction is going to be disrotatory. End orbitals have opposite sign, reaction is going to be conrotatory. That is the picture that you see. If the highest occupied molecular orbitals, end orbitals have same sign, reaction is going to be disrotatory. If they have opposite sign, reaction is going to be conrotatory. Okay. When I do photochemical reaction, what happens? Electron from HOMO goes into LUMO. So, for the photochemical reaction, the original LUMO has now become HOMO. For photochemical reaction, original LUMO is now the HOMO. Okay. So, then let us look at this. What are the signs of the end orbitals? Both have the same sign. What did we say? If both have the same sign, reaction is going to be disrotatory. So, the 4 electron photochemical reaction is going to be disrotatory. In the 6 electron, end orbitals now have opposite sign. Therefore, photochemical reaction is going to be conrotatory. 8 electron end orbitals have same sign, so reaction is going to be disrotatory. 12 electrons end orbitals have same sign, so reaction is going to be disrotatory. So, 6 electrons, 10 electrons end orbitals have opposite sign for the photochemical reaction. Therefore, reaction is going to be conrotatory. Oh. So, the important features that we have established are, we have used nodes to write the orbitals of hexatriene. In case of ethylene, ethylene going to butadiene, 2 goes to 4, so we can write orbitals. 4 going to 8, you combine 2 butadienes, you can write 8 orbitals of octatriene. 16, 8 plus 8 is going to be 16. 12, 6 plus 6 is going to be 12. So, if I know 6, I can write the orbitals for 12 electron system. But when I want to write for 6, I could not do it in that way. And therefore, for 6, we have used the concept of nodes. Then we made some kind of rule of thumb, write all the homos, and then we have a simple way of writing homo. Plus, plus, minus, minus, plus, plus, minus, minus is the easy way to write homo. Then we try to write some rule of thumb for going to LUMO. And when you do the LUMO, what is the trick? Plus, minus, minus, plus, plus, minus, minus, plus, plus, and change the sign. So, we learn this. Then for the thermal reaction, what do we see? End orbitals have opposite sign, reaction is going to be conrotated. If they have same sign, reaction is going to be disrotated. In the photochemical reaction, the original LUMO has now become HOMO, and apply the same principles to it, and you can get this. Okay. This was sort of rules of thumb. Can we make a deeper analysis? So, we are going to make we are going to analyze the conversion of cyclobutene to butadiene. When I want to analyze this reaction, I can look from going from cyclobutene to butadiene, that is the ring opening, or I can also analyze it butadiene going to cyclobutene. This is what we called as the principle of microscopic reversibility. You can analyze forward reaction, you can analyze back reaction, both results should be the same. Okay. So, when I do this, which are the reacting orbitals of cyclobutene? So, one orbital is the double bond, and the other reacting orbitals is this. So, our 4 orbitals are going to be sigma, pi, pi star, and sigma star in increasing order of energy. Why is sigma the most stable? Because it is formed by head-on overlap, strongest orbital. Why is sigma star the most unstable? We are breaking a strong bond. Therefore, sigma star is going to be like. Okay. How did we make? What are the 4 orbitals of butadiene? Psi 1, psi 2, psi 3, and psi 4. These are going to be the 4 orbitals of butadiene. Okay. So, let us draw those 4 orbitals. This is your psi 1 orbital, plus, 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 plus. Plus, plus, minus, minus. That is your psi 2 orbital. Psi 3 orbital will be plus, minus, minus, plus, and your psi 4 orbital will be plus, minus, plus, minus. Okay. All right. So, we are going to make what is called as a correlation diagram. So, first part of the correlation diagram, that is your sigma, that is your sigma star, that is your pi, that is your pi star. When we combine two pi orbitals to make psi 1, what will we find? Pi 1 plus pi 2 orbital decreases in energy. So, psi 1 is of lower energy than pi, psi 2 is of higher energy than pi, because it is pi 1 minus pi 2 gives you this. Similarly, pi 1 star plus pi 2 star gives you psi 3, pi 1 star minus pi 4 star gives you psi 4. So, pi is between psi 1 and psi 2, pi star is between psi 3 and psi 4. Okay. So, we are now analyzing butadiene going to cyclobutene. Okay. This is, we are drawing the correlation diagram for the disrotatory process. Disrotatory means thumbs must move in opposite direction. Okay. So, this is moving in what direction? Clockwise. This is moving in anti-clockwise manner. So, what is the result? Plus and minus. So, this rotatory process will give you sigma star. Looking at end orbitals, this rotatory process will give you sigma star. Look at the middle orbitals. What is the sign of the middle orbitals? The sign of the middle orbitals is same sign. And what is the sign of pi? Pi is also same sign. Therefore, your psi 1 orbital, can overlap with sigma star, or it can overlap with pi. Psi 1 orbital can overlap with this. If you look at end orbitals, when I do this rotatory process, I will get sigma star. All right. So, your psi 1 orbital can overlap with sigma star or with pi. Which is the orbital of lowest energy? The orbital of lowest energy is pi. This is called the principle of minimum crossing. When I can correlate with two different orbitals, I always correlate with the orbital of lowest energy. So, I can correlate with sigma star or pi. I will then correlate with pi. What did I do? I am so sorry. Okay. This which I did was con-rotatory process. I am sorry. Okay. So, sorry. This rotatory will give you plus and plus. When I do the disrotatory process, it will give you bonding. So, I can correlate with sigma. When I look at middle orbitals, I can correlate with pi. So, I can correlate either with sigma or pi. Sigma is the lowest. Therefore, I will correlate with sigma. All right, everybody is okay? Let us repeat. When I look at middle orbitals and move it in disrotatory fashion, this moving clockwise, this moving anti-clockwise, it will give me sigma orbital. When I look at middle orbitals have the same sign, that is just like pi. Therefore, psi 1 can correlate with sigma or pi. Sigma is the orbital of lowest energy, therefore, I correlate with sigma. Okay. Then I look at my psi 2 orbital. When I do the disrotatory process, what will happen? Plus will come here, minus will come here. So, it will correlate with sigma star. So, psi 2 will correlate with sigma star. When I look at the middle orbitals have opposite signs, and that is going to be, this is your pi, this is your pi star. So, middle orbitals will correlate with pi star. So, end orbitals will correlate with sigma star, middle orbitals will correlate with pi star. Once again, orbital of lowest energy is pi star. So, I correlate with pi star. Then I look at psi 3. This rotatory process, just like this, will give me bonding orbital. So, psi 3 can correlate with sigma. If I look at middle orbitals, what is the sign? Sign is the same. Therefore, I can correlate with pi. But now what is the problem? Sigma is already occupied. Therefore, I cannot correlate with sigma. Therefore, I correlate with pi. So, psi 3 is correlated with pi. When I look at sigma star, picture is like this for the end orbital, plus and minus, this rotatory process will give me correlation with sigma star. So, psi 4 will correlate with sigma star. When I look at middle orbitals have opposite sign. Therefore, it will correlate with pi star. But pi star is already occupied. Therefore, it will correlate with sigma star. So, this is going to be your correlation diagram. Okay. What is the ground state of butadiene? In the ground state of butadiene, for the thermal reaction, 2 electrons in psi 1, 2 electrons in psi 2. Where do these psi 1 electrons go? Psi 1 electrons go into sigma. So, psi 1 electrons go into sigma. How many electrons? 2 electrons. Where does your psi 2 electron go? Psi 2 electrons go into pi star. Pi star 2 electron. This is ground state. This is not the ground state. Therefore, thermal reaction disrotatory is not allowed. If ground state gives ground state, reaction is allowed. If ground state does not give ground state, reaction is disallowed. Okay. Let us look at photochemical reaction. What happens in photochemical reaction? One electron from Psi2 goes into Psi3. Therefore, Psi1 2, Psi2 1, Psi3 1. What is this? First excited state. This is my own short form, please. First excited state. Okay. Where are these electrons going to go? Where will your Psi1 electron go? Psi1 2 electrons will go into sigma. Psi2 1 electron will go into pi star. Where will your Psi3 1 electron go? It will go into pi. First excited state has given first excited state. Therefore, photochemical reaction is allowed. All right. So, that is the picture that we can do for this. All right. Let us summarize what we did. We wrote the orbitals Psi1, Psi2, Psi3, Psi4. When I made the disrotatory process, Psi1 can correlate with sigma. If I look at middle orbitals, Psi1 correlates with pi. So, Psi1 can correlate either with sigma or with pi. Principle of minimum crossing tells me that I should correlate with the lowest energy. Therefore, of the two options, I correlated with sigma. When I look at Psi2, when I look at end orbitals and do disrotatory process, what will happen? It will give me anti-bonding orbital. So, Psi2 in disrotatory process will correlate with sigma star. When I look at middle orbitals have opposite signs, therefore, it is correlating with pi star. Therefore, your Psi2 is correlating either with sigma star or pi star. Pi star is lower in energy, therefore, we correlated with pi star. When I look at Psi3, do the disrotatory process, it will correlate with sigma. So, one of the correlations is with sigma. When I look at middle orbitals have same sign, therefore, it correlates with pi. Sigma is already occupied, Psi1 has gone to sigma, therefore, Psi3 can only go to pi. When I look at Psi4, picture is like this, therefore, when I do disrotatory process, it will correlate with sigma star. So, Psi4 can correlate with sigma star. When I look at middle orbitals have opposite signs, therefore, it is going to correlate with pi star. But pi star is already occupied, therefore, I correlated with sigma star. So, I made this correlation diagram. Then I saw what happens in the thermal reaction. My thermal reaction will have 2 electrons in psi 1, 2 electrons in psi 2. So, we wrote this psi 1 2, psi 2 2. Psi 1 2 electrons went into sigma, psi 2 2 electrons went into pi star. So, this is ground state, this is not ground state, therefore, reaction is disallowed. What is the ground state? Sigma 2 pi 2. Then I did photochemical. I excited 1 electron from psi 2 to psi 3. Therefore, my first excited state was psi 1 2, psi 2 1, psi 3 1. Psi 1 2 went into sigma, psi 2 1 went into pi star, psi 3 1 went into pi. First excited state gives first excited state. Therefore, photochemical reaction is allowed. Okay. On this side, we are making the correlation diagram for the conrotatory process. Lowest orbital sigma, highest orbital sigma star, pi, pi star. These will be your 2 bonding, those will be your 2 anti-bonding. Psi 1 is below pi, psi 2 is above pi, psi 3 is below pi star, psi 4 is above pi. This also now explains what? When I look at UV of ethylene, what am I doing? Electron from pi is going to pi star. So, what is the energy? So much energy is required. When I do butadiene, what happens? Electron from psi 2 going to psi 3, less energy required. Therefore, butadiene absorbs at 217, ethylene absorbs at 185. Okay. All right. Now, we are going to look at the conrotatory process. What will happen? This will move clockwise, this will move clockwise. So, plus will be outside. What will be inside? Minus will be inside. So, in the conrotatory process, psi 1 will correlate with sigma star. Psi 1 will correlate with sigma star. Look at the middle orbitals. Middle orbitals have same sign. Therefore, it will correlate with pi. So, psi 1 will correlate with sigma star or pi. Pi is the orbital of lowest energy. Therefore, I will correlate with pi. Look at psi 2. Conrotatory process, this will come here, this will go here. Therefore, it can correlate with sigma. So, psi 2 will correlate with sigma. Look at middle orbitals. Middle orbitals have opposite sign. Therefore, it correlates with. Your pi had the lowest, so I correlated with pi. Your sigma is the lowest, so I correlate with this. Psi 3 picture is just like psi 1 picture. Therefore, conrotatory will give me anti-bonding. So, it will correlate with sigma star. Look at the middle orbitals. Middle orbitals have same sign. So, it will correlate with pi. But pi is occupied. Therefore, I will correlate with this. So, psi 3 will correlate with sigma star, psi 4 conrotatory will correlate with sigma, sigma is unfortunately occupied, therefore, I look at middle orbitals have opposite signs, it correlates with pi star. So, that is going to be my correlation diagram, right. Okay. So, we did this. Now, thermal reaction psi 1 2 psi 2 2. Where are these electrons going to go is psi 1 2 is going to go into pi, psi 2 2 is going to go into sigma. Ground state has given ground state, therefore, thermal reaction is going to be allowed. What will happen in photochemical? Electron from psi 2 will go into psi 3. So, psi 1 2, psi 2 1, psi 3 1. Where will these electrons go? Yes, please. Where will these electrons go? Psi 1 2 will go into pi. Do not say only pi, pi 2, all right. 2 electrons from psi 1 will go into 2 electrons in pi. Where will your psi 2 1 electron go? Psi 2 1 electron will go into sigma. So, sigma 1 electron. And where will your psi 3 1 electron go? It will go into sigma star. So, it is equivalent to exciting 1 electron from here into sigma star. So, first excited state has given very high energy excited state. Therefore, photochemical reaction is disallowed. All right, everybody is okay? Let us quickly repeat. When I look at psi 1, conrotatory process will correlate with sigma star. Looking at middle orbitals, it will correlate with pi. I correlate with pi because pi is the orbital of lower energy. Psi 2 orbital conrotatory process will correlate with sigma. Middle orbitals have opposite signs, therefore, it will correlate with pi star. Sigma has lowest, therefore, I correlate with sigma. Psi 3 in similar fashion, conrotatory process will correlate with sigma star. When I look at middle orbitals, same sign, so correlates with pi, but pi is occupied, therefore, I correlate with sigma star. Psi 4 conrotatory process will correlate with sigma, but sigma is already occupied. Therefore, I look at middle orbitals have opposite signs, therefore, it correlates with pi. Then we wrote psi 1 2, psi 2 2 ground state goes into psi 2 2, pi 2 ground state gives ground state. Therefore, thermal reaction conrotatory is allowed. Photochemical, we shifted 1 electron from psi 2 to psi 3, psi 1 2 went into pi, psi 2 1 went into sigma 1, and psi 3 1 went into sigma star. So, it is equivalent of exciting one electron from sigma into sigma star. That is a very high energy excited state. So, thermal reaction con-rotatory is allowed, dis-rotatory is not allowed. Photochemical reaction, dis-rotatory is allowed, con-rotatory is not allowed. Okay. So, we analyze the reaction going from butadiene to cyclobutene. Now, we are analyzing the reaction going from cyclobutene to butadiene. Okay. Dis-rotatory process. Your thumbs are moving in opposite direction. Therefore, your end orbitals have same sign. Therefore, it correlates with either psi 1 or psi 3. Psi 1 has same sign end orbital, psi 3 has same sign. So, your sigma orbital can correlate with psi 1 or psi 3. Psi 1 is lower in energy, therefore, I correlate with this. Okay. Then I look at the pi orbital. When I look at the pi orbitals, what do I see? The pi orbitals have same sign, therefore, it will correlate with psi 1, middle orbital same sign, or with psi 3. So, I can correlate with psi 1 or psi 3. Psi 1 is occupied, therefore, I correlate with psi 3. So, let us rub this out. So, your psi 1 correlated with this, your pi correlated with psi 3. As you will see, picture is going to be exactly the same. All right. Now, let us look at what is our next orbital? Pi star. Pi star orbital have opposite signs. Therefore, it can correlate with this psi 2 or psi 4. So, pi star orbital can correlate with psi 2 or psi 4. Psi 2 is lower, therefore, pi star will correlate with psi 2. I look at sigma star. This rotatory, what do I see? It will give me plus here, minus here. Therefore, it can correlate either with psi 2 or psi 4. Sigma star can correlate with psi 2 or psi 4. Psi 2 is occupied, so I correlate with psi 4. Okay. What is your ground state? thermal reaction sigma 2 pi 2. Sigma 2 will go into, sigma 2 will go into psi 1 2. Pi 2 will go relate into psi 3. This is ground state, this is not ground state, therefore disallow. Photochemical sigma 2 pi 1 pi star 1. Sigma 2 will go into psi 1, pi 1 will go into psi 3, pi star 1 will go into psi 2. Psi 1 2, psi 2 1, psi 3 1, first excited state as given, first excited. So, whatever correlation diagram you got for butadiene to cyclobutene, same correlation diagram you get for cyclobutene to butadiene. Thermal reaction, ground state does not give ground state, therefore, disrotatory is not allowed. First excited state gives first excited state, therefore, photochemical reaction is allowed. Okay. All right. Now, we do the conrotatory process. When I do conrotatory process, what will happen? Plus will go here, plus will come here. Therefore, this will be minus. Therefore, end orbitals have got opposite signs. End orbitals will have opposite signs with psi 2 or psi 4. Sigma will correlate with psi 2 or psi 4. Psi 2 is lower in energy, therefore, I correlate with psi 2. I look at pi orbitals. What do I see? Pi orbitals, same sign. Therefore, it can correlate with psi 1 or psi 3. So, pi orbitals will correlate with psi 1 or psi 3. Psi 1 is lower in energy, therefore, we did. So, sigma is correlated with psi 2, pi is correlated with psi 1. All right. Look at pi star. Pi star is plus and minus, therefore, it can correlate with psi 2 or psi 4. So, pi star will correlate with psi 2 or psi 4. Psi 2 is occupied, therefore, I correlate with psi 4. I look at sigma star. Sigma star, what is the picture? Let's look at the picture of sigma star. Okay. This rotatory process, plus will be here, minus will be here, therefore, plus will be here. Therefore, it can correlate with psi 1 or psi 3. All right. So, psi 1 or psi 3, psi 1 is occupied, so I correlate with psi 2. Okay. So, thermal reaction sigma 2 pi 2. Where does sigma go? Sigma goes into psi 2. And where does pi go? Pi goes into psi 1. Ground state has given ground state. Look at that. Whichever way I go, ground state gives me ground state. So, sigma 2 pi 1 pi star 1. Sigma 2 goes into psi 2 2. Pi 1 goes into psi 1 1 and psi 3 1, sorry, pi star 1 goes into psi 4 1. It is exciting an electron from first psi orbital into fourth psi orbital. So, first excited state gives high energy excited. So, whether I look from butadiene to cyclobutene or cyclobutene to butadiene, answer comes out 4 electron thermal reaction is going to be conrotatory. Photochemical reaction is going to be disrotatory. We will have a little break and come back. Now, we are going to make our going to analyze this reaction using frontier molecular orbitals. This is the approach used by Ken, Ichi, Fukui. As I said last time, he shared the Nobel Prize with Roald Hoffman. Okay? That's Ken, Ichi, Fukui using the frontier molecular orbital approach. We are looking at the ring forming reaction. So, our first ring forming reaction is going to be butadiene going to cyclobutene. So, we are going to write HOMO. What is the HOMO of butadiene? Butadiene has 4 orbitals, psi 1, psi 2, psi 3, psi 4. So, your HOMO is 4 divided by 2, your HOMO is going to be psi 2. Plus, plus, minus, minus. Make the disrotatory process. Move the orbitals in opposite direction. What is the result? Plus will be here, minus will be here. So, disrotatory gives you anti-bonding. Therefore, disallowed. Make the conrotatory process. Plus will come here, minus will go there. So, con-rotatory will give me bonding. Therefore, con-rotatory is the allowed process. In the orbital analysis, we required about 35 minutes. Here, in 1 minute, we have the answer. Look at the HOMO, see what happens. Very simple. Okay. If I look at the photochemical reaction, what will happen? Electron from highest occupied molecular orbital will go to lowest unoccupied molecule. So, the HOMO of the photochemical reaction is going to be psi 3, which was your original LUMO. So, what is the sign of psi 3? Plus, minus, minus, plus. This rotatory plus will overlap with plus. This rotatory will give me bonding. Automatically, con-rotatory will give me anti-bonding. So, in the butadiene case, thermal reaction HOMO is psi 2. This rotatory gives me anti-bonding, con-rotatory gives me bonding. Therefore, the 4 electron reaction is going to be thermal, is going to be con-rotatory. When I do photochemical, electron from psi 2 will go to psi 3. Therefore, your HOMO is now going to be psi 3. Do the disk rotatory process, the disk rotatory process will give me bonding. So, as simple as that. Okay. Hexatriene going to cyclohexadiene. What is the HOMO of hexatriene? Hexatriene will have 6 orbitals. So, divide by 2, your HOMO is going to be phi 3. HOMO for the thermal reaction is going to be phi 3. Plus, plus, minus, minus, sorry, plus, plus. This rotatory will give you bonding. Therefore, your 6 electron reaction, thermal reaction will be this rotatory. If anybody has a problem, please don't keep quiet. Okay. When I do photochemical, what will happen? Electron from phi 3 will go into phi 4. So, the HOMO of the photochemical reaction is going to be phi 4. What is phi 4? Phi 4 is your original LUMO. How do I write LUMO? Plus, minus, minus, plus, plus, minus. This rotatory will give me anti-bonding. Con-rotatory will give me bonding. Therefore, 6 electron photochemical reaction is going to be con-rotatory. Octatetraene going to cyclooctatriene. Octatetraene has how many orbitals? 8 orbitals. Therefore, your HOMO is going to be 4th orbital. HOMO for the thermal reaction is going to be theta 4. How is going to write theta 4? Plus, plus, minus, minus, plus, plus, minus, minus. End orbitals have opposite signs. This rotatory will give me anti-bonding. Con-rotatory will give me bonding. Therefore, 8 electron thermal reaction, con-rotatory is allowed. HOMO for the photochemical reaction. Electron from theta 4 is going to go into theta 5. What is theta 5? Theta 5 is your original LUMO. Plus, minus, minus, plus, plus, minus, minus, plus. This rotatory will give me bonding. Whenever the end lobes have same sign, this rotatory will give me bonding. Whenever end lobes have opposite signs, it will give me, this rotatory will give me anti-bonding, con-rotatory will give me bonding. So, very simple. You ask to write any picture, we can write picture for this. So, within 5 minutes, 4 electron system, 6 electron system, 8 electron system, 10 electron system will be very similar. The end orbitals will be plus plus, minus minus, plus plus, minus minus, plus plus. End orbital will be same sign. Therefore, thermal reaction will be distributed. Now we are looking at the ring opening reaction. There is a lot of mathematics to this. Being organic chemists, we forget the mathematics. Okay, we tell what's the last answer. All right. So, HOMO of one component and LUMO of the other component. So, you draw this. What are your components? So, your component is a sigma orbital and a pi orbital. Okay. So, for your cyclobutene going to butadiene, what are your two components? One is a sigma orbital, one is a pi orbital. So, take the HOMO of this. What is the HOMO of the sigma orbital? There are two orbitals, sigma and sigma star. So, your HOMO is going to be sigma star. Sorry, HOMO is going to be sigma. Let me put it like this. I think that will be better. HOMO of the carbon-carbon single bond is going to be sigma. And according to what we said here, we will use HOMO of one component, LUMO of the other. So, what is the LUMO of the carbon-carbon double bond? The LUMO of the carbon-carbon double bond will be pi star. Okay. So, this is your HOMO, which is sigma, and this is your LUMO, which is pi star. What is this process that I am doing? Is it conrotatory? Is it disrotatory? Disrotatory. Plus and minus, plus and plus. Which are the new bonds we have formed? All right. What type of bond is this? Plus and plus. This is bonding. What type of this thing is this? This is anti-bonding. One bonding, one anti-bonding. Therefore, disallowed. We do the conrotatory process. That's your pi star. Plus and plus. This is going anti-clockwise. This is going clockwise. This is plus, this orbital is plus. So, conrotatory process gives me two bonding. Therefore, is allowed. Then somebody will say, all right, you move this one anti-clockwise, you move this one also anti-clockwise. Now move both of them clockwise. So, move this clockwise, move this clockwise. Sorry, this is anti-bonding, this is anti-bonding. 2 anti-bonding is also allowed. 2 bonding is all right, 2 anti-bonding is all right. 1 bonding, 1 anti-bonding is disallowed. If I multiply 2 numbers which are positive, my answer is positive. If I multiply 2 numbers which are negative, my answer is still positive. But 1 positive, 1 negative, answer is negative. So 2 bonding is allowed, 2 anti-bonding is allowed, 1 bonding, 1 anti-bonding is disallowed. Then somebody will say, I said, well, why not do opposite? You knew the answer, therefore you went like this. So let us do opposite. Carbon-carbon, single bond, LUMO. So, sigma star. Carbon-carbon, double bond, HOMO. So now pi, that's your HOMO, plus and plus. Your LUMO is sigma star plus and minus. This rotatory process. So this will be plus. So this is bonding. This will be minus. 1 bonding, 1 anti-bonding. Therefore, this rotatory is disallowed. Do con-rotatory process. All right, plus and minus. This I moved anti-clock. This will also move anti-clock. Plus and plus, plus, bonding, minus will come here. This is bonding. So whether I take HOMO of the single bond and LUMO of the double bond, or HOMO of the double bond, LUMO of the single bond, answer is still the same. Okay. What about photo? All right. Just now we looked at the thermal reaction. Now we'll look at the photochemical reaction. HOMO of the excited carbon-carbon bond. When I excite carbon-carbon double bond, what will happen? Pi will become pi star. And LUMO of this, that's going to be sigma star. So I always take the HOMO of the system that I excite. I excited the double bond, so I took HOMO of the excited double bond. So I should draw the picture involving sigma star and pi star. It's the HOMO of the excited ethylene. And sigma star plus and minus. This rotatory plus and minus plus This rotatory will give me both bonding. Somebody would say that let us excite this. Okay. So excite the carbon-carbon single bond. What is the HOMO of the excited carbon-carbon single bond? Sigma star. And LUMO of this. So that's going to be pi star. So whatever happens, picture will be sigma star and pi star. Okay. All right. Sorry, cyclohexadiene. Going to hexatriene. What are my two components? One component is carbon-carbon single bond. What is the other component? Other component is butadiene. Okay. So carbon-carbon single bond will take LUMO. So that's going to be sigma star. Butadiene, HOMO is going to be Psi2. So for the thermal reaction, my picture will involve plus plus minus minus. Open it, disrotatory. This will be plus, this will be minus. The new bond, plus and plus, bonding. Minus and minus, bonding. So this rotatory will give me both bonding. I look only at the new bonds that are formed. So this rotatory gives me two bonding. Therefore, okay. So that was your thermal picture. What did we do? Psi2 was your HOMO, sigma star was your LUMO. Okay. Now let's look at photochemical. Butadiene is excited. What is the HOMO of the excited butadiene? Psi1, Psi2, Psi3, Psi4. Normal butadiene, 2 electrons in Psi2. When you excite it, 1 electron will go into Psi3. So the HOMO of the excited butadiene is Psi3. So your picture will involve Psi3 what is Psi3? Plus, minus, minus, plus. Plus and minus. Open it in disrotatory manner. This is plus, this is plus, so this is bonding. This is plus, this is minus, so this is anti-bonding. This rotatory gives me one bonding, one anti-bond. Con-rotatory will give me 2 bonding or 2 anti-bond. Therefore, con-rotatory is law. What does this emphasize? You must be able to write HOMO and LUMO. This is what we have to emphasize. That's the trick. Okay. Let's look at our final example. Cyclooctatriene. What are the components? Carbon-carbon bond. What is this component? This component is hexatriene. Carbon-carbon bond, LUMO, sigma star. Hexatriene, HOMO is phi 3. So, sigma star. Plus plus, minus minus, plus plus. So this is plus and this is plus. This is plus and this is minus. One bonding, one anti-bonding. Therefore, in the 8 electron system, this rotatory is disallowed. In the photochemical, carbon-carbon, LUMO is sigma star. Hexatriene excited, HOMO is phi 4. Okay. So, phi 4 plus, minus, minus, plus, plus, minus. So this is plus, bonding. This is minus, this is also minus. So photochemical reaction, you will get both bonding. So in half an hour, we looked at 4 electron system, 6 electron system, 8 electron. You can multiply 10, 12, 14, you can do it. All you have to do is go on drawing pictures. Okay. So, in the FMO analysis, we first looked at the ring forming reaction, and then we looked at the ring opening reaction. In the ring opening, HOMO of one and LUMO of the other. In the ring forming, you look only at the HOMO of the open chain structures. All right? Okay. Now we are going to our conservation of orbital symmetry. Woodward and Hoffman (1981) Nobel Prize was shared by these two people. All right. Woodward had already won the Nobel Prize earlier. So, for Pericyclic, Nobel Prize was shared by these two people, 1981. The orbital symmetry approach is a very much more complete approach. The FMO approach is a shortcut. And in shortcut, most of the times we get the correct answer. But later on we will see a few examples where orbital symmetry gives you correct answer. The frontier molecular orbital doesn't give you the correct answer. So, let's look at this conservation of orbital symmetry. Okay. What is this the model of? Yes? Expected wrong answer was cyclohexane. All right? This is your benzene model. Okay? Pi cloud above, pi cloud below. Okay. All right. Okay. All right. So, this is your psi 1 orbital, plus, 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 bottom all minus. Okay. Now, we are looking at the symmetry of these orbitals. What is this? Mirror plane symmetry. All right. Normally, when we write MP, it usually means melting point. Okay. Here, this is we are talking of mirror plane symmetry. All right. What is this? Is it symmetric or is it anti-symmetric? It's going to be symmetric. Okay. So, this is one symmetry element, and this is the other, what is called as the C2 axis of symmetry. We are going to rotate around this point. What have we got? All positives are on the top. When I do this, all negatives are on the top. Therefore, for C2 axis of symmetry, it is anti-symmetry. All right? That's your mirror plane symmetry, and C2, you rotate around the middle carbon-carbon bond. Okay. All. What can you say about mirror plane symmetry? It is not symmetric. Okay. Now let's look at C2 axis. What is on the left hand side? Plus. On the right hand side, minus. Plus, minus. So, for C2 axis of symmetry, it is symmetric. Plus, minus, minus, plus. Mirror plane, it is symmetric. C2 axis, rotate it. Starting was plus, after rotation starting is minus. Therefore, it is anti-symmetric. Plus, minus, plus, minus. Mirror plane, it is not symmetric. With a model it's easy, but suppose I ask you without the model, what's the way to do it? First and last is opposite, second and second last is opposite. Automatically, it means C2 is symmetric. All right, so that's it. First and last is opposite, second and second last is opposite. Therefore, it should be symmetric. What did we start with? Plus, plus, minus, plus, minus. So, C2 axis is symmetric. In fact, it is very easy. In the open chain conjugated systems, mirror planes start with S. S, A, S, A, S, A, S, A, S, A, go on writing. For C2, A, S, A, S, A, S. No A, S, S. Okay? A, S, A, S or S, A, S, A. All right? So that's very simple. Even without any common sense, you simply write. That's a simple way to do it. Okay. Now, let's look at our next one. Okay. So, this is your sigma orbital. What can you see? Mirror plane, it is symmetric. Minus, plus, plus, minus. C2 axis, minus, plus, plus, minus. So, for both, sigma is symmetric. So, this is your sigma star orbital, plus and minus. Mirror plane, not symmetric. C2 also not symmetric. So, anti-symmetric with regard to both. So, your 4 orbitals of butadiene are psi 1, psi 2, psi 3, psi 4. And your 4 orbitals of cyclobutadiene, sigma, sigma star, pi, pi star. Mirror plane, symmetric, C2 anti-symmetric, mirror plane anti-symmetric, C2 symmetric. Okay. So, we are ready to do this. Now, we look at something here. We are going to open this in disrotatory manner. Just now there is mirror plane, all right. Move it like this, there is a mirror plane. Move it like this, mirror plane. Move it like this, mirror plane. So, the disrotatory opening is associated with a mirror plane symmetry, all right. Do this, there is a mirror plane, mirror plane, mirror plane, mirror plane, mirror plane. So, the disrotatory process is associated with a mirror plane symmetry. Let us show that. The disrotatory process is associated with a mirror plane symmetry. Okay. When I look at the conrotatory process, now we are looking at the center of symmetry. Open it. What do we see? This goes up, this goes down. This goes up, this goes down. So, all through there is a center of symmetry. So, the conrotatory process is associated with a C2 axis of symmetry. C2 axis corresponds to a center of symmetry. Center of symmetry. Center of symmetry. So, when I do the correlation diagram for the disrotatory process, I am going to look at the mirror plane symmetry. When I do the correlation diagram for the conrotatory process, I am going to use C2 axis of symmetry. Okay. Sigma, pi, pi star, sigma star, psi 1, psi 2, psi 3, psi 4. I want to emphasize one important feature. All right. Suppose I put a substituent here, a carbon substituent. Then this is not symmetric. We are not looking at symmetry of molecule. We are looking only at the symmetry of the orbitals. Substituents don't count. We are looking at orbital symmetry. So whether there is methyl here or here, it doesn't make any difference. We are not looking at symmetry of molecule. We are looking at the symmetry of the orbitals. Okay? It's a orbital symmetry, not molecule symmetry. All right? Therefore, substituents don't enter the picture at all. Okay. All right. So, this rotatory means mirror plane symmetry. Even without looking on the blackboard, there S, A, S, A. For double bonded systems, this will also be S, this will also be A. But the crucial thing is, sigma is symmetric for both, sigma star is anti-symmetric for both. Now we are going to join orbitals of like symmetry. Okay. So when I look at sigma, it is symmetric. Therefore, I can join to psi 1 or psi 3. But psi 1 has lowest energy, so principle of minimum crossing tells me that I will join with psi 1. When I look at pi, it is symmetric. Therefore, I can join to psi 1 or psi 3. Psi 1 is occupied, therefore, I will join it to psi 3. Look at this, pi star is anti-symmetric. If it is anti-symmetric, I can join it only to psi 2 or psi 4. Since psi 2 is the orbital of lowest energy, I join it to psi 2. And sigma star is anti-symmetric, so I can join to psi 4 or psi 2. Psi 2 is occupied, therefore I join it to psi 4. You will see that this correlation diagram is exactly the same as we did for orbital analysis. Joining is exactly the same. Whether I join from this side, whether I join from this side, story is the same. Psi 1 is symmetric. Therefore, it can join to sigma or to pi. Sigma is lower, so I join it to this. Psi 2 is anti-symmetric. Therefore, I can join it to pi star or to sigma star. Pi star is lower, so I join it to this. Psi 3 is symmetric, so I can join it to pi or to sigma star. I'm sorry, sigma. Sigma is occupied, so I join it to pi. And psi 4 is anti-symmetric, so I can join it to sigma star or I can join it to pi star. Pi star is occupied, therefore I join it to this. So, we have reached this. Now, let us look at this. We are going from butadiene to cyclobutene. What is our ground state? Thermal reaction psi 1 to psi 2. Psi 1 2 goes into sigma Psi 2 goes into pi star. Ground state, not ground state. Therefore, disallowed. Photochemical reaction. Psi 1 2, Psi 2 1, Psi 3 1. Psi 1 2 goes into sigma, Psi 2 1 goes into pi star 1, Psi 3 1 goes into pi 1. First excited state gives first excited state. Therefore, photochemical reaction is disrotatory. Thermal reaction, disrotatory, is not allowed. Okay. Cyclobutane going to butadiene. Thermal reaction. Sigma 2 pi 2. Where does sigma go? Sigma goes into psi 1. And where does pi go? Pi goes into psi 3. Ground state, not ground state, therefore disallowed. Photochemical reaction. Sigma 2 pi 1 pi star 1. Sigma 2 goes into psi 1 2, pi 1 goes into psi 3 1, pi star 1 goes into psi 2 1. First excited state gives first excited state. Therefore, reaction is allowed. Okay. When we meet next week, we will take up the Horn rotatory process.